Now we are gonna implement the same what we have read in a two-area system. We'll try to implement the same in MATLAB. Okay, I'm gonna take a new simulating model. Okay, I'm gonna take a new simulating model for you now. Yeah. Yeah, I'm going to take a blank model now, and I'll start with our conventional things, what we have learned so far. I'm going to search for the library. So first of all, let me have a single area system. The commonly used blocks, I do have two constants and three transfer functions, isn't it? And I use it to have two summers, and I use it to have one scope, and I use it to have three transfer functions, 1, 2, and 3, and one gain. This what I needed for a single area system, isn't it? Yes. Yeah, this was our single area system, isn't it? So I'm going to feed the values also now itself. This is what is this one? PC of S. This was PD of S, isn't it? And this was the speed garner. I'm going to represent it as SG1. Okay, and this is I'm going to represent it as T1. Okay, and this is I'm going to represent it as PG1. Okay, this is PG1. So what are the values which I have employed last time? This was I have taken it as 0.5. This I have taken it as 4, I think. Yeah. This I have taken it as, and this I can take it as 0.5, and this I'm going to take it as 100, and this is somewhere around 20 because it is a little bit higher time constant of uh, the generator load model. This was 1 by 3, right? So in order to overcome this one, okay, in order to overcome this manual controller, what I have done here actually, I have implemented, yeah, an integrator here, isn't it? So I have taken some value of 0.09, and yeah, and I have provided this one as a negative. This was a single area system which we have done already, isn't it? Now we are gonna do this one for a two area system. Now what was the output here, guys? This was F1 of S, right? So now I'm gonna take the same one for my second area. So if you carefully see what I'm doing, you can easily understand. So I'll take new values here. Okay. I'll yeah. If you carefully see, again I'm doing the same. Okay. Yeah, this was area 1 on your left hand side, and this was area 2 on your right hand side. This is speed governor 2, which represents the second system. This is turbine 2. Yeah. And this represents my parts. Yes, sorry. This is my speed governor, right? This is my speed governor. This is my turbine. Okay. This is my yes. This is my SG speed governor model. SG2. This was the gain. I'm taking just two similar systems. Okay. So I'm gonna take the same values again for you. Here 0.5, and this is 4, and this will be for the turbine, a similar turbine, which is just like the first area, and the generator also was same. Yes. Now both are exact replicas. This is area 1, this is area 2. Now what I'm doing now, I'm going to take these two. Sorry, I'm going to remove these two. See this, what I should do, I should take a summer now. Yeah, this is summer plus yes. Yeah, this is delta F1 of S, isn't it? What is this one? This is F1 of S, right? This is F1 of S, and from here, what I'll be getting? I'll be getting F2 of S. What is this one? Both are to be joined. I'm gonna bring it down a little bit. Yeah, both are to be joined, and it is to be fed to a block, isn't it? So I need a block now again, a simple transfer function block. So I'm going to take one more transfer function block. This represents a tie line, isn't it? This used to represent a tie line model. It was of the formula of 2 pi. We had it on the board, 2 pi t1 2 by s, isn't it? So I'm going to take some random value. I'll take it as 0.5 by, okay. Okay, this was the Thailand model. So what I should do, I should give it as a feedback to this one, isn't it? But here I already have it, this one. So what I'll be doing is I'll be mentioning it as, yeah. So what I'll be doing, so I'll remove this one and I'll place it here. Okay. What is this one, guys? Yeah. What is this one? This is PD of S, right? This is our demand of area 1, isn't it? And here also I'll do the same. I'll place it here. Also I'll make it as a minus. This is PD2. Now this is fed back as, what is this one, guys? This is P transmission line 1 2 of S, isn't it? Now the same is to be fed back to my second area also, but I must use a negative value. So I'm going to take this one, I'm going to give it as -1. Okay. Yeah. And I'm going to give it as, yeah, 1 minute. Yeah. What is this one? This is P tie 2 1 of S, isn't it? Now, apart from that, what I have mentioned for you, I'm supposed to use a, see now, this is the system, right? Now let's see a continuous dashboard, fine, 1 minute. There must be a scope. Yeah. I'm going to watch my frequency change, and also I'm going to watch my, yeah. So I'm going to take 4 inputs now. Let's see how this is going to perform. I have just taken an integral controller of only single area variable. See, only delta F1 of S is being fed back as an integral controller. See, now I'm considering that there is a change in area 1, just 0.1, 10% change. Okay. The top one indicates the change in demand of area 1. This indicates a change in demand of F1. Okay. I'll mention here. Yeah. And this is my, see, second area, I have not done anything. Second area is very calm. Now I'm going to run this one. And let's see, I'm going to run this one for 100 seconds. Okay. Stop. See, 1 minute. Yeah. There is a change in area of demand of 1. See, the frequency is increasing at a very greater rate. Even at area 2 also the frequency is varying, even though there is no change in the demand. The frequency is varying a lot, isn't it? See, have I, let me check if I have done any mistake. Yeah. No, it is fine. Right. So now what I'm gonna do now, so if I give this one as an integral feedback again, this tie line also, then my system may stabilize, isn't it? So now what I'm gonna do, I'm gonna give this one also as a feedback. Okay. So what I'll be doing, instead of giving this one here, instead of giving two integral feedback controllers, what I'll do is here, I'll use a summary. Yeah. This is minus, this is minus, because there is already a negative here. I'll take it as some point 5. You can vary this value based upon your request. See what I have done, apart from this controller, integral controller, I have taken this p tie also as an integral controller. See, this is also now being fed as an integral controller. The same way I'm going to implement it here also. I'm going to bring it here. Yes. And I'm going to use the same summer here. Yes. Now let's check. Okay, let me check whether there is error. Why my frequency is varying a lot. D1 by D2. This is negative feedback. This is also negative feedback. Minus of 2. This is minus 1. Let me take another model which I have already simulated for you. Okay. See, this is what we are simulating now. Here, instead of this 0.5, I'm going to take this. Okay. See now. See, my values are now settling down, area and F1. What I have done, just nothing. See guys, these values are your choice. I have just adjusted this value, 2 pi T12. Instead, earlier it was 0.5, now I have adjusted to 0.2. See, for a change in demand in area 1, both the frequencies are settling down, if you carefully see. Area and frequency 1 is settling down, area and frequency 2 is also settling down after experiencing a transient. Since the demand is at area 1, the transient is a little bit higher in area 1. Here it is a little bit lower. Now, let's see if this one, if I give a huge change in demand, 0.3. Now, let's see whether it is gonna, yes, again it is settling down. The steady state values are both 0. Now, let's see if it is gonna work for changes at both the things. Now, here also I'm giving 20% change in demand in area 2 also. See, both, even though here it is 0.2, here it is 0.3, 30% change in demand in area 1, 20% change in demand in area 2. Even though there are changes in demand in area 1 and 2, both the frequencies are settling down finally. This is the advantage of giving an integral controller of tie line power also to the system. So apart from this one, I have kept this one as 0.425, this one as 0.2. So this is the advantage. Okay, if I give it this one as a feedback with an integral action, then my, see, if you want, I'll show this one. Even I will go to 120% variation. Okay, just I'm gonna for 120% variation. Even if I go for 120% variation also, maybe the transient is a little bit higher, but finally my frequency is settling down, isn't it? This is the advantage of providing integral action. That's it, guys. Thank you. I'll upload this one to your courseware, this model also. Okay, this is two area control. We have started with the modeling of transmission line. We have implemented in MATLAB. We have seen this, how this integral controller action is going to work to improve our steady state values. So in single area system, we have taken area controller error as only change in frequency. But in two area system, what is the area control error, guys? We are considering the change in frequency and also the change in tie line power also. Both we are feeding it as a feedback, isn't it? So integral feedback is the summation of change in frequency and also the change in tie line power. Okay, that is the integral value which we are giving it as a feedback. So that's it, guys. Thank you. So the final call of today's class is for a two area system, or for a multiple area system. It's not only that we should give an integral feedback of frequency, change in frequency. It's better if we give an integral feedback of tie line powers also, so that my steady state value of frequency will reduce to 0. Okay. Thank you. Thank you for joining, guys. We'll meet again in the next class with tutorials. There are small problems on tutorials on regulations of frequencies. So we'll do that in the next class. Okay. Thank you as of now.